Hey everyone, and thanks to everyone that watched my previous video on Kickstart. That was a bit of fun, and now we've got Codejam 2022 starting. So well done everyone that participated in the qualifiers, and I hope some of you are qualified and maybe even trying to win a Codejam t-shirt. And yeah, I'd love to try win another Codejam t-shirt. It's been a while. I got the Hacker Cup one a couple of years ago, so that was nice. So I'll go through this chain reactions problem because they had a slightly different way of doing it. In their analysis, they've suggested using depth first search, whereas I use topological sort, which is quite a nice way of doing things. So I'll go through topological sort and how I solved it. But first I'll just go over the problem quickly. Or you can just read it here if you like. But basically you're given a tree or a forest of modules, and you have to pick a module that doesn't have any dependencies to start with. So here you've got two choices. You could start from module 4, which is worth 50 points, so you could start from module 3, which is worth 40 points. And you basically once you start a module, you take a pathway all the way to the end, and you take the maximum of that pathway. So you take 60. So if you started with 50 first, you'd get 60, and then you'd start with 40 next, and 60 is already taken, so then you get 40, which is the maximum of that pathway. The pathway just keeps going until you get to the end, or until you get to a module that's already been done. So that means your score would be, I think they calculated it here, yeah, 60 plus 40, which is 100, which if you did it in a different order, you did 40 first and then 50, then you'd get the 60, and then your final path would be 50 to 20, and the maximum is 50, so then you get 50 plus 60, which is 110. And so yeah, to me this looks like topological sort. I mean, you could think about it in terms of a tree, and you're going from, I mean, in this case, from left to right, or you could start from the right hand side and go, you know, what's the maximum of this subtree, what's the maximum of this subtree, and so on. But it is good to think of it as a tree. I'll just quickly go through topological sort for those that haven't seen it before. And with Rust, there's a nice topological sort implementation by Kinku. So she's got some nice code here. So I just copied and pasted this and just changed a couple of lines, and Bob's your uncle. We had a solution that worked first time, so that was nice. So quickly, I'll just spend like 1 or 2 minutes going over topological sort and then the solution, and then I'll go to the code. So let's just say you've got a tree. I'll show you some arrows. So, and each of these arrows can be thought of as a dependency. Okay, so topological sort, there's a few ways of doing topological sorting. You can just look it up on Wikipedia, but it's pretty simple. You just look for any node that doesn't have any dependencies, and that's something you could start off with. So we could start off with this one, or this one, this one, or this one, because they don't have dependencies. This one would be like the worst one to try to start off with, because you'd be blocked, because this one is doing before it, and so on. So let's just start off with this one here, and then next we could take this one because it's no longer got a dependency if we've taken this one, but we'll just take this one, and then we'll take this one and take this one. So you can imagine it's a little bit like breadth first search. Like we could be adding these to a stack, and or a queue rather, and actually it doesn't matter which. So you can do breadth first or depth first, but the key is, the main thing to know is, if for each node, if we count how many dependencies it has, or the end degree. So the end degree of this one here would be 2, because it's got 2 nodes going into it. So we can never process a node until its end degree becomes 0. So all these ones I mentioned had end degree 0, so that's fine. And once we took this, since this one would have had end degree 1, now once we take this, we change its end degree to 0. So now this one we can take, and then this one has end degree 0, so we could take that. And now what's interesting is this one has end degree 0, because it would have had end degree 2, but we subtracted this one and this one, so now this one's 0, so we can take that, we can take this, we can take this, and then we can finally take that. So that's topological sort. It's a way of sorting the nodes based on how many dependencies they are. And it has some nice properties, and it's useful in other situations. In our situation, we had some values, and we're trying to get as many maximums as we can in a way. So if it was just one path, it'd be easy. We'd just take the maximum in that pathway. But the hard part is once we get to a junction, it's like, how do we proceed? So for example, let's say, like, do we go along this way? Or do we go along this way? So it's obvious if we're coming along here, we'll just keep taking the maximum to maximize our score until we get to here, and then we're not sure. And likewise, we'd keep taking the maximum until we get to here. And then once we get to here, so I'll just write in some numbers to make this a bit more clear. So let's say we had 5 and then 10. Let's say here we have 7. Then let's just say, I'll add another edge just to make it more clear. Let's say we have 8 here. Then let's just say we start with this 8. So we know we get to here and we're like, okay, 8's better than 5, so we keep the 8. And then 8's worse than 10, so we'll keep the 10. And then here there's nothing previous, so we'll just keep the 7. And now going forward, we think, well, we can try to get lucky and increase the 7, or we could try to increase the 10. But we can't go forward with both these paths. So it makes sense that we go forward with the 7, because that's got more chance to improve. And then this 10 will add to our total score. So we'll have our score over here equals 10 plus. And then this 7, like say here we had like a 4. 7's bigger than 4, so we'd take the 7. So this will become a 7. Let's say here is a 3, and then this is a 2, so we take the 3. And now it's like, what do we take, the 3 or the 7 at this junction? So we'll take the 7 into our score, because more chance of improving the 3 kind of thing. And let's say this was 12 here, so 12's not as good as 3, so we'll just keep the 12. And actually maybe it would have been good if there's a few more junctions here, because it's not always going to be 2. So let's just say we had another value here, which was 4. So now instead of taking the 7, we're taking the 7 plus we'll take the 4. So 3 is the worst. So we'll take the 3 to here. Since we have 12, 12 is better than 3. So that'll just be 12. and so this is a 2, so 12 is better than 2, so plus 12, and then finally we'd have a 2 here, and let's just say this was a 1, so 2 is better, so let's make that a 2, so, and then, so we'll just take the 2 because it's the last value. So that's a bit of an edge case, is if we, if there's nothing to go to, then we just take the value we currently have as the maximum. So here's the topological sorting code. So it's just a graph or an adjacency list, and then they topologically sort it and they get the nodes sorted. So this would be like node 0, node 1 goes to 2, and so on. So we're just going to parse the input here, turn it into a graph. We don't actually need to sort the nodes, but as we go through the nodes in topological order, we can calculate the things here. So let's look at the code quickly, just to see how they sort the nodes. So they just reference the graph immutably as a slice. Get the length of the graph. They calculate the in degree. So for every node that's got a node going to it, they increase the in degree by 1. Then they go through all nodes 0 to n. If the in degree is 0, then they add it to a queue. So that's these nodes we were talking about that have 0 in degree. So all of those will be in the queue. And now, while the queue has an item at the front, we just pop that. So it's kind of like breadth first search, which is usually a bit more useful. And then for each item that comes after that arrow is pointing to, so V is pointing to next. So now next in degree will be subtracted by 1. And if the in degree is 0, then that means that item's ready to process it, so we'll add it to the queue. So so my code basically just copied this code, just O to n went down. So I just paused the input. The only bug I had was I forgot to subtract 1 from here, but I parsed the input into a graph. So I have these points. So I'm scanning the input using this scanner reader writer, which I also took from her GitHub repository. So let's just look at that quickly. So for each test case, we get the number of nodes, or modules we could say. We scan a vector called fun, which is the amount of fun of each module, and we're trying to maximize the amount of fun. So the ith value of this is how much fun the ith module is. And then this is just saying, this is a vector where the ith value is the node that the ith node points to. So that's why for the ith node, so I'm adding this, whatever points at me, I'm adding to my adjacency list. Is that right? Yeah. I see. Yeah. So it's actually pointing the other way around. So if this is a 0, then it doesn't point at anything. So we don't do anything. Otherwise, I is pointing at something. So whatever we pointed at, we add it to I's adjacency list. So yeah, this is like a directed graph. And then we just topologically sort. So we pass a reference to the graph, and I pass I don't pass a reference to this fun array. So we actually want topological sort to take ownership of this because it's going to modify it in place. And as I mentioned, there's times where we update the value to be the maximum that we've found so far. So let's have a look at this method, and then you would just get the result back from this. So n is the length of the graph. We have this vector of minimums, which was necessary because, for example, when we had these, when we're trying to calculate this one, it was the minimum, which was 3, which was going to propagate. 12 ended up being bigger than 3 anyway, but 3 was the minimum of 4, 7, and 3. So that's why we need to keep track of the minimum. We also need to keep track of the total of this, because the amount we add to the score is the total minus the minimum. So yeah, we're keeping track of the minimum and the total at each of the nodes. So this is getting the n degree. This is adding to the queue the nodes that have no dependencies, or in degree 0. And yeah, we start off our answer as 0. I usually use 64 just because I don't want overflows. So yeah, if the node V has no children, so it's not pointing at anything, so it's just pointing off into the abyss, which means we'll just take that maximum value. So we'll just increase answer by that. Otherwise, we'll loop through all of its dependencies, subtract 1 from the n degree, as we mentioned before, and then the total of the next item, we'll add our maximum to the total, which is like saying, where 7 plus 4 plus 3, we'll get a total of 14. And the minimum, so the minimum of the nodes leading up to this node here would be 3. So we're keeping track of the minimum. And once we finally are ready to process that node, we add to the answer just the total of all the nodes leading into that node minus the minimum, which will propagate through. And then the next, like my current value, will become my current value, or the maximum of the maximized with the minimum of all the values leading into it. So that was just, is 12 bigger than 3? Okay, we'll keep 12. Otherwise, if this was like a 1, then this would have become a 3. And then, yeah, we just add the next value. Since it's no longer getting any dependencies, we can add it to the queue, and that means we can continue on. And yeah, that was it. So I thought that was just a fun little satisfying problem. It wasn't overly difficult. If you've seen a topological sort before, then it's just more of an exercise to get it implemented. But yeah, I hope that just shows how topological sort can be useful. And yeah, just wish everyone good luck for the rest of the competition. And I won't go over the rest of the problems. I was a bit frustrated with the last problem because I did pass all the test cases in the judge. I just had a really simple solution where I just estimated the average in degree, and it passed the offline interactive judge. But then the online judge, obviously they made the test cases harder by creating graphs that had bigger clusters. So there were some nodes that had that you could miss that had a lot of connections, and so yeah, I was trying to do it without walking down any passages because I thought maybe they'd just randomly generate graphs, but obviously they generated some hard test cases, so I would have actually needed to walk to a few. But yeah, I've had a few other things on this weekend, and this dice one, that was a fun one. It was, I think, reasonably straightforward. The rough solution here was just to read the set of die, sort them and then just have a count. And each time we get a larger dice than the current count or the current length, we can increase the length by 1. So that was pretty straightforward. But yeah, thanks for watching the video. Feel happy to subscribe, and I hope you all get a Codejam t-shirt. I'll try with my Codejam t-shirt for the next video I make. And yeah, feel free to comment and all that. Have a good rest of your weekend, everyone. I'll see you next time.